So I will give an overview talk on astrophysical relativity group. So the gravitational waves, these are, as you know, is a prediction of general theory of relativity, and these are the solution for a linearized Einstein equation. And these are actually the ripples in the curvature of space-time and propagates at the speed of light. And then gravitational waves are radiated by massive objects whose motion involves that undergoes accelerated motion, provided the motion is not perfectly spherically symmetric. So what are the promising astrophysical sources for gravitational waves? So broadly, the astrophysical sources of gravitational wave can be categorized into four. One is a transient signal from compact binary objects, like compact binary is composed of black holes or neutron stars. So these are the sources what we have seen so far in LIGO and Virgo. And another type of source is are spinning neutron stars. This will produce a continuous gravitational signal. And the third type of source is burst signals, burst gravitational signal expected from gravitational collapse of collapses like supernova explosion, etc. And fourth type is stochastic background signal. The origin of such signal can be either cosmological or astrophysical. Cosmological in the sense that it could be originated from the early universe. So then what we have seen so far. So LIGO and Virgo has seen at least 10 binary black hole mergers and 1 binary neutron star mergers in their O1 and O2 run. So then now the O3 run is going on. So we are expecting more events in the coming months. So here you see the gravitational wave observed in these are the wave form the binary black hole the first binary black hole merger signal we saw in 2 LIGO detectors, and this is a distribution of masses for the black holes and neutron stars we have seen so far, and here the blue ones are observed in the gravitational wave window. And here, these are the black holes we see in the gravitational wave window, and this is the neutron star merger we see in LIGO and Virgo. And what you see, the remaining black holes are we observe in electromagnetic window, basically the X-ray binaries. And there are other neutron stars that we see through electromagnetic observation. So what are the activities in the astrophysical relativity group at ICTS? So the activities here in ICTS can be broadly classified into 3 categories. One is probing strong gravity using gravitational wave data. That includes testing general relativity and also probing the nature of black holes and other compact objects. And second category is doing astrophysics using the gravitational data. That includes inferring the formation channels of binary black holes and searching for gravitational lensing signatures in the gravitational wave window and understanding the properties of lenses. And third category is source modeling. That includes actually, that basically includes making more accurate template waveform for the search of binary black hole mergers by combining analytical and numerical relativity models. So I will first describe the first part, like the probing strong gravity. So the one project we explore is one test on general relativity. It's called the in-spiral merger ring down consistency test. So basically, this is a signal we expect from a merging binary black hole. So while the black holes merge, it undergoes basically different phases. One is it's in spiral around each other, that's in spiral piece. Then finally it merge and ring down. So we can divide this entire signal into basically 3 parts, basically in spiral, merger, and ring down. So the way we are searching for such signal is basically we are checking the phase. We use a technique called match filtering, where we are matching the phase of the template waveform with the actual data. So any deviation from underlying theory will modify the template waveform. You will see a modification in the template waveform. So when we search or estimate the parameters of these binary black hole merger events, if the underlying theory is different from GR, then there will be systematic deviation from the estimated parameters. So the idea behind this test is we divide the template signal, template waveform into 2 parts. One is the in-spiral part, another is the post-in-spiral part. These are actually, the templates are based on GR. Then we estimate the parameters of this, any binary black hole merger event using either just in-spiral part of the waveform and then post-in-spiral part of the waveform. Then check for the consistency between these parameters. The parameters obtained from the in-spiral analysis and the post-in-spiral analysis. Here, the parameters we are using for this analysis is the spin and the mass of the final black hole. So here is a sample plot. Actually, this is a plot from the first observed event. So here is a posterior. These dash curves are posteriors of final spin and final mass obtained from post-in-spiral part and in-spiral part, and the dark contour is the black contour is from the joint analysis. So you can see there the parameters are consistent. The obtained parameters are consistent with each other. So then these are the latest results from the analysis. So here you can see, actually, as I have mentioned earlier, in O1 and O2, you have seen 10 binary black hole mergers, and here what we have done is that instead of plotting individually like final mass and spin, what we have done is we have plotted the posteriors of the relative difference in the mass and spin obtained in using in-spiral and post-in-spiral templates. And ideally, it should be at 0 if GR is correct, and otherwise it will deviate from 0. So these colored contours are for different events listed here, and the shaded region is a combined posterior. Basically, we can combine the posterior of delta MF and delta F. That is represented by the shaded region. And actually, you can see that that is actually consistent with GR, is peaking around 0. So then another test we are developing is a no-hair test for binary black hole mergers. So the basic idea is actually the gravitational the waveform expected from binary black holes mergers has a multipole structure. So what we are checking is that this multipole structure, whether is consistent with GR or not. We have the data, then we estimate the parameter of these events using different modes of the waveform and check for the consistency. This is analogous to a no-hair test that is actually based on consistency between different quasi-normal modes. So here you can see a sample plot from this paper. Basically, what we have done is that we check the relative difference between the chip mass and mass ratio computed from quadrupole mode of the waveform and non-quadrupole mode of the waveforms. Those looks consistent. And for more details on this project, you please see Tausif's poster. And then another project is inferring the true nature of the compact objects. So the basic question we are asking is, we have reported 10 binary black hole mergers. The question is actually, are we indeed observe binary black holes, or some other object, some exotic object that actually mimics as black holes? So the fundamental difference, one fundamental difference between the black holes and black hole mimickers would be their tidal deformability. So the black hole mimickers can get tidally deformed when they approach to each other, as shown in this figure. Then that will induce a quadrupole moment. Here you can see the Qij is a tidally induced quadrupole moment, and lambda is the quadrupole moment parameter. Sorry, the tidal deformability parameter, and epsilon ij is the tidal field. And then what we do is that we use the new verb form that includes tidal deformability. So basically, when we include the tidal deformability into the analysis, then the verb form will be different from what we expect from binary black hole mergers. Then we use an in-spiral verb form for a tidal deformed binary system, and estimate the tidal deformability parameter using such templates, and use constraint obtained from such analysis to put constraint on the properties of the exotic or black hole mimickers. For example, here, what we did is that we obtained the constraint on the tidal deformability parameter, and using that constraint, assuming that the mimicker is a boson, is a pair of boson stars, then we put constraint on the boson star properties. That is a boson mass and a coupling constant. So these are dashed regions. Both the dashed regions are ruled out by such analysis for a sample injected over form. So next section is astrophysics using gravitational data. So the first project is understanding the formation channels of the BBH mergers observed by the LIGO and Virgo. So in the coming months, we are expected to observe hundreds of binary black hole mergers in the ground-based detectors. And such mergers are basically produced in different through different formation channels. And these are some examples. The isolated binary evolution. These are produced by either by merging of primordial black holes, or dynamical formation in globular cluster, etc. So the difference between the the black holes produced through different formation channels will have a different parameter distribution. For example, here you can see this is a distribution of mass and redshift of black holes produced in isolated binary evolution, and this is the distribution of mass and redshift for the black holes produced in from POP3 stars. So then, with this observed mass and redshift distribution from the binary black hole mergers observed by LIGO and Virgo, we can infer what is the underlying formation channel that produces these objects. So we are developing a Bayesian model selection technique to distinguish between various formation channels of these underlying models. So you can see more details on this project in Pariza's poster. So another project, another ambitious project we are exploring is on the electromagnetic counterpart of neutron star, binary neutron star mergers. As you know, like when we observed the first neutron star merger in LIGO and Virgo, we have also observed a kilonova associated with that. So then basically the kilonovas are very similar to type 1 supernovae in many sense. Kilonovas are produced by the merging neutron star, merging of neutron stars. On the other hand, type 1a supernovae is produced by merging of white dwarfs. And both are produced by the radioactive decay of our process elements. And in type 1a supernovae, people have observed that there is a relation between the, actually if you check the light curve, that how the luminosity of this supernovae changes over time, then people have observed that the peak luminosity is related to, there's a universal relation between peak luminosity and the change in luminosity over a fixed time. So this is a universal relation. You can use this universal relation and to make use the type 1a supernovae as a standardizable candles. That means that you can measure the luminosity distance very accurately. So the question we are asking is, can such a relation exist for kilonovaes also? Yeah. So then, what we have observed is actually, at least in theory, if you use the theoretical models, such relation exists, and the publication is in preparation, and you can see Rahul's poster for more details on this project. So another set of projects we are exploring is searching for the gravitational lensing signatures in gravitational wave data. And this is the one of lensing projects. Here what we are looking for is strong lensing of gravitational wave due to the intermediate galaxies. So if the gravitational waves from binary black hole mergers lens by intermediate galaxies like this, what happens is that it will produce multiple signals. We will be able to observe multiple signals from the same merger event with same parameters at different time, because this will be taking different paths. So the time delays varies from hours to months. So then we have developed a Bayesian-based Bayesian model selection technique to identify such pair of events in the events observed by LIGO and Virgo. So here is a results from the first O1, O2 data. And these are actually the Bayesian likelihood for individual pairs of events. Actually, I quantify the confidence for them, these pairs to be a lensed pairs of events from a single binary black hole mergers. Actually, the total Bayesian likelihood ratio is actually sum of these two quantities, is a log of these factors. And you can see that these are the significant levels. As this value increases, that the significance of these pairs to be lensed events of a single merger increases, and you can see all the even pairs are below 2 sigma level. So we didn't see much significance for the significance for any of the pairs we have observed in O1, O2 data is very small, so for being lensed. And this paper is already published, and this is an article came in Scientific American based on these results. And you can see Ajit's presentation for more details on this project. Then there are a couple of projects running based on gravitational lensing, and basically if you observe multiple images of same binary black hole merger due to lensing by galaxies, then this actually can be used to improve the parameter estimation of such events. If we are combining with the electromagnetic survey data, we can pinpoint the location of such merger event. And also we can use this data to break the degeneracy and obtain the gravitational polarization of such events. And another project we are looking into is constraining the fraction of dark matter in the form of compact objects using the gravitational wave data. Basically what happened is that the compact objects are one of the prominent candidates for dark matter. So if they are present, then what happened is the incoming gravitational wave can be lensed by such compact objects, and then the observed gravitational events will be, the observed signal will be deformed like this. Actually, you can see the blue one is the unlensed event, and the other curves are the lensed gravitational wave amplitudes when the signal is lensed by various different lenses. And search for such lens events, and if we can compute the rate of such lens events, then we can use that to put the constraint on dark matter fraction in the form of nachos. This work is in progress, and you can see Pradim's poster for more details. The last part, gravitational source modeling. And as I have mentioned, actually, the method we are using for searching and doing the parameter estimation of gravitational waves is a kind of a phase matching technique. We have a template, and we check for the matching of this template with the data. So the accurate phase modeling of this gravitational wave templates are very essential to get a accurate to estimate the parameters accurately. And see here, what I have shown is actually, as I mentioned, this gravitational wave has a multipole structure. So then the dominant mode is a quadrupole mode, and here what I have shown is that the the shaded region is a region where the higher modes, other than the quadrupole mode, is necessary to do a accurate parameter estimation of binary black hole mergers. And x-axis and y-axis are the total mass and mass ratio of this the binary black holes. And you can see these various curves denotes the spin parameters, and whatever the area above this curved region, it denotes a region where the systematic error due to the lack of higher modes in the template will causes a systematic bias in the estimated parameters. So to do a proper parameter estimation in these regions, we need to include higher modes in the template waveform. So here, what we are doing is actually we are trying to incorporate higher modes in the waveforms by combining the analytical model. There's a PN approximation models along with the NR data, and then combine them phenomenologically and comes up with a analytical phenomenological waveform model. So this project is led by Ajit Mehta, and there are 2 publications on this project. And we are also checking how these new waveforms, including the extra parameters, are impacting the parameter estimation and test of GR. This work is in progress. And that pretty much summarizes the activities in the group, and thank you.